Let's continue with our lecture on interpretable and generative AI in computational pathology. So, in the first part of today's lecture, or lecture 5, what we saw was how we can the different kinds of techniques that we have actually developed to bring in interpretability to foundation models. So, like we saw, there are so many of these different foundation models that are out there, but these foundation models they lack in interpretability and explainability. However, there are methods like these handcrafted feature engineering methods, or there are these concept-based methods. These these concepts or these language-based concepts that are more appreciated or better appreciated by clinicians. So, how can we marry foundation models with more handcrafted approaches to make these integrated approaches more interpretable? So, that is what we saw in the first half or in lecture 5. So, in lecture 6, we will be focusing on the generative AI aspect. So, obviously, since in today's day and age of AI, a lot of things are centered around Gen AI, so it would be criminal not to talk about Gen AI, right? So, we've been doing a lot of that in our work as well, not just in radiology, like you saw on day 1 of the GYAN series, where we showed how we can use some text-based prompts to generate images, and also we saw how we can infuse eye gaze patterns to make these generated images better. So, similarly, we have also been working on different generative AI approaches for digital pathology as well. You'll get these slides, so you can always scan this, and you'll see our GitHub repo for a lot of our work that we have done on Gen AI. That's not exhaustive, but those are some of our published works. So, one of the challenges in computational pathology that we discussed yesterday was out of focus areas, right? So, similar to that, you have problems like low resolution image. What does that mean? So, one of the first steps of getting a slide digitized is, mounting that slide, or preparing that slide on or preparing the tissue on your glass slide, sticking that into your scanner, and then getting it digitized, right? So, this scanner, end of the day, you'll have like a microscope, you'll have different objective lenses, right? So, end of the day, what you have is you have different powered lenses, and based on that, and that would decide what quality or what resolution that slide has been scanned at. So, like we saw yesterday, you can have slide scanners all the way from 5x to a couple 100x. The better the scanner or more high resolution the scanner is, the more expensive it is, right? So, we want to make sure that we have, obviously, it's good to have high resolution scanners, but it's not always practical. There are cost issues. Not all centers might be able to afford these scanners. However, there are basic versions of the scanners that are at low resolution, which, let's say, a digital pathology center should be able to acquire. Now, let's say that we have an image that has been taken at 5x, right? And we saw that in the foundation models, and there was this question yesterday, what resolution do we train these models on, like 5x, 10x, 20x, 40x, 50x, whatever. So, if you have a model trained on 20x images or 40x images, but the images that you have right now that are collected at your digital pathology center, that's only at 5x, we can apply a 20x trained foundation model on 5x, but obviously the results that we get will be suboptimal, right? Because these images were trained at different resolutions. What does that mean? Should we throw these images away? No, we can still use these images. And how do we use these images? There are techniques called super resolution techniques, where we can super resolve a lower resolution to a higher resolution. So, today I will be talking about, or in this particular work, I will be talking about some of the Gen AI methods that we have developed to super resolve low quality, low resolution images to high resolution images. So, this was published last year in Medical Image Analysis. Uh, Before this, there were multiple different works in generative adversarial networks or GANs that had done that. But if you want to get into GANs and generative AI, you'll see that GAN methods have their own issues. Where there's mode collapse, a lot of times you cannot really work with high dimensional data and so on and so forth. A lot of that problem has been solved with diffusion models. So diffusion models are essentially models that start with noise and progressively denoise it, and then you get an image from it, or you get a denoised data from it. I won't really go into details of how diffusion models work, but what diffusion models let us do is one of the important or one of the flexible you know approaches there, or one of the functionalities that diffusion models have, is we can condition the diffusion models with multiple different kinds of conditions, and these are called conditional diffusion models. So the goal is to go from an image what you see on your left of your screen to an image what you see on your right of your screen. Now, so by the way, if you look at these images and you have different kinds of primitives here, what is the difference that you see in the low res image and the high res image? Anyone? Show of hands. So what are some of the visually, what are some of the differences that you can observe? Everyone can observe this difference. Okay, can we have a mic here, please?
The edges are blurry.
The edges are blurry. Yes, good. On the left image, right?
Yeah.
As compared to the right. What else?
The morphology is more clear for
The
the
morphology is
cells.
clear, so you can see the cells clearly.
Yeah, and also the staining, we can see the staining properly, like which are more dark and which are light. So
Yes.
based on that, the nucleus positions and all this that can
Yeah.
be
Good.
told. And also another thing, the proximity of those cells, like from left side image, it is not clear the proximity of the cells, like two cells, their distance between them.
Right.
But from right side, it is very clear to see the proximity of those cells.
Right. So that again ties back to the first answer, the edges of the cells. So because the edges are clear, you can clearly see how close the cells are with respect to each other. And you're right, you can actually observe the shape of the cells, the morphology of the cells, the texture of the cells. Right. So if you look at this one right here, I mean, I don't know if this is a cell or not, maybe it's a gland, but you can clearly see that you don't see the texture well here, but you see the texture quite clearly here, right? And if you want to apply your not just your foundation models on this image, not just your foundation models, but you want to apply your handcrafted features, it's very difficult to expect that your handcrafted features will be able to extract something meaningful here. You don't have the shape of the nuclei, you don't have the structure, you don't have the texture. I mean, if you don't have that, you can't reliably identify the centroid of the nuclei, which means your graph methods will suffer. So everything breaks down, right? So in order to make sure that that does not happen, the first step is we super resolve the image and then apply our techniques on the super resolved image. So is that clear? So why we need super resolved image or good quality images? So moving on. So what we did was we trained a super resolution technique, and then these are some of the results that we got on prostate cancer and on lung cancer. And I'll talk about what's happening here. So if you look at, so HR stands for high resolution. So these are the original high resolution images. You can clearly see that the structure of the nuclei is quite clear. You see what's happening with the other tissue regions and so on and so forth. You see the dark nuclei here. So for the lung cancer case, but these are the low resolution images in the second column. So the goal is to develop techniques that can take your low resolution images and generate these high resolution images. So that's what we want to do. And like I said, there are existing methods, or there were existing methods back then, and these were mostly based on GANs, generative adversarial networks, that could do this. And you can clearly see that these methods have been able to super resolve these images quite well. And here are the results of our method. And since they look so similar to each other, it's obviously difficult to appreciate the quality directly by looking at this. I mean, obviously you can look at the difference between BSR GAN and our method, and or BSR GAN and SwinIR GAN. It's quite clear that it's quite blurry here, it's less blurry here, but eventually we would want to quantify it, right? If you don't quantify it just qualitatively, it's difficult to say which method is better. So one of the metrics that is used to quantify, for those of you who are from signal processing background, you would be familiar with the concept of signal to noise ratio, right? So you have a particular signal, and then you have a noise. You can always look at the signal to noise ratio, and then higher signal to noise ratio is usually good, right? Another metric that is used, or one of the most common metrics that is used in generative AI is called FID. So it's called a Fréchet inception distance. So using the FID scores, we can actually quantify how good the generated image is. However, the case I'd like to make here is, some of the existing methods like, PSNR or SSIM. PSNR is, peak signal to noise ratio, or you have SSIM, which looks at the structural similarity. So these might be methods, or these might be metrics that are good for real images, or not real images, for natural images, but these are not methods that are optimal, or these are not metrics that are optimal for pathology images, and I'll show you why. So same thing, we have low resolution images here, we have high resolution images here, and here you have different kinds of super resolution techniques. So bicubic interpolation. So bicubic interpolation is a very easy method. So you basically take pixels and you interpolate the values so that you get something that's closer to, let's say you take an average of pixels or something like that. So it's a very simple method. So, and you clearly see from a visual perspective, the bicubic interpolated image looks worse than our image, right? The image that we have super resolved. I don't know if this is clear here, probably not. Maybe you have to look at the YouTube link. I think you should do that now just to appreciate it. So this is very visual. When it comes to Gen AI stuff, everything is very visual. So if you look at it closely, and you'll see it in the slides tomorrow, the bicubic interpolated image is hazy. I'm assuming some of you can actually see it. It's hazy, and our image that you see here, it's quite clear, or even some of the images that have been generated by the GAN methods, they're quite clear. But look at the signal to noise ratio. So the bicubic interpolation method has a signal to noise ratio of 27, and our method, or some of the GAN methods, have signal to noise ratio that are lower than that, right? So this means that something is going on where, even though perceptually the GAN based methods or the more sophisticated methods look better, but from a quantitative perspective they don't, right? Which means that this tells you that there's something going on with the evaluation metrics. Now here's again, like with a number of other things that we have spoken about over the last 2 to 3 days, there's an important lesson. You will be using different kinds of metrics for your analysis, but make sure you understand what these metrics are, because for your purpose, for your evaluation purpose, those might not be the best metric. And don't just go with metrics that people have been using without really understanding, because there will be times where you know that your method is performing well, but your metric does not reflect it, and this is a classic example of that. So what we did was, first of all, we realized that this is not the best metric to go with. So we needed to design better domain specific evaluation metrics. And in our case, the evaluation metrics, or the domain that we needed to design this metric for, is digital pathology. So when it comes to digitized pathology images, or these histopathology images, what are the different objects of interest? You have the nuclei, you have, let's say you have the stroma, you have the epithelia, you have other kinds of glands and whatnot, but eventually everything comes down to nuclei and background, correct? So it's important that when you generate these super resolved images, the texture, so you mentioned that the texture was bad, or you mentioned that the edges were not clear. So we want to ensure that the super resolved images are as close in texture and shape as possible to the super resolved images should be as close in shape and texture as possible to the real high quality images, right? So that's the eventual goal. So in order to achieve that, what did we do, or what was our metric? So we have the high resolution image, we have the low resolution image. So if you're interested in working with these images, there are models out there like HoverNet, which I briefly mentioned a couple days ago, and there are other models, more recent models like CellVIT. So you can take these models and you can extract the location of the nuclei, you can extract the boundaries of the nuclei, and this is what it is. So you extract where the nuclei is. So the white regions represent the nuclei and the dark regions are essentially the background. And you can overlay the nuclei boundaries on the high resolution image. And then you have your low resolution image. We use our method, which is, so this was a previous version. It's called SuperDiff now. So we take that method and we super resolve it. So ISR is the super resolution image, or the super resolved image coming from the low resolution image, right? So you can clearly see that this looks very similar to the high resolution image. Now what we do is we take the nuclear segmentations that were obtained from the original high resolution image and transfer it to the super resolved images. Ideally, if the reconstruction or if the super resolution works fine, the location of the nuclei should exactly be the same, right? The location should not change, right? So if this is the low resolution image, this is the corresponding, this is the high resolution image, this is the super resolved image. If a nuclei is in this location here, it should be exactly in that same location. The location should not change. So that's why you take the locations of the nuclei from the ground truth, you overlay the locations to the super resolved image, and you look at if there is any change in the intensity or if there is any change in the texture of the nuclei, right? So if the images are close, then the changes, or let's say the interhistogram distances between the intensities and the texture will be very small, like they will be as close to each other as possible. So which means that is a metric we should use for our analysis rather than signal to noise ratio or some of the other metrics. Okay, and that's exactly what we did here. So then we compared our state of the art GAN methods against our method, which was SuperDiff, and we had different GAN methods. We had the bicubic interpolation method. We applied it on different cancers. We had prostate cancer, lung cancer, brain cancer, and we had different data sets as well. We had 100 cases here, 2,000 cases here. So based on that, if you just focus on the texture, so L1 is essentially a distance metric, right? So you have two different points. You just look at the L1 distance. So if you look at the L1 distance with respect to texture or intensity, lower the distance, the better it is. We find that our method was a lot better compared to the GAN methods. Now, how do these generated images look like, let's say, not for super resolution image, but for another application where you want to generate synthetic images? So remember, we had this discussion where we saw that if you do not have enough training data, one of the ways in which we can augment our training data set is through generative AI, right? So you can use certain conditions, you can generate these synthetic samples, you can provide these samples to your deep learning model or to your machine learning model, and you can train this with real samples plus synthetic samples with the expectation that the new model will be better than the model that saw a very limited quantity of data, right? And that's one of the applications. I'll talk about that in the next slide, how it was useful. But here's just a representation, an example of how well we could do this. This was a workshop paper at MICAI 2023. We used a diffusion autoencoder for generating these images. On the top row here, so this entire block is colorectal cancer. On the top row here, you see real examples of different types or different categories or different let's say subtypes of this colorectal cancer, where you had normal mucosa, lymphocytes, or different regions rather. These are not subtypes. Let's not call it subtypes, because when you call subtypes, it means that there's some molecular subtyping involved. It's just the different locations. So you have lymphocytes, you have mucus, you have smooth muscle, stroma, tumor, and then the second row, what we show here are synthesized examples. Now just compare the first row to the second row. You'll see that the second row, the images that we generate are quite similar to the images that you have in the first row, and these were verified by our pathologist. So if you look at our paper, you'll also see we have a small section there where our pathologist talks about what they think the differences are between the two sets of images, how similar they are, where we are going wrong, and all of that. So you'll see that section there. But at a high level, you can see that we have been able to do a good job in synthesizing these images, right? And that's not true for just colorectal cancer. The model that we trained, we also had examples of breast cancer as well, and you see that here. For breast cancer, we had normal cells, we had metastatic cells, and you see that we have been able to generate it quite well. So now, how do we use it? So what's the downstream analysis that we performed on this data set? So this is a Chaoyang data set. It's freely available. If you want to work on simple classification problems, I would recommend you to just look up this data set and see if you can train these models. You can apply foundational models, you can extract features and run simple models to distinguish between normal. So it has, I think, 4 categories, normal, serrated, adenocarcinoma, and adenoma. So feel free to play around with this model. So back then, we picked this model because it had multiple classes. So it was a good model to start with, but nowadays you have, it was a good data set to start with. Nowadays you have you have larger data sets. Yeah, but anyways, so the goal was to see if we could train our model on the training set and evaluate it on the test set to distinguish the 4 different categories that you have here. Now, if you look at the table, so there's something very interesting happening here. If you train your model, your classification model, I don't really remember the specifics of what classification model we used. It's there in the paper. So you take the features from your feature extractor, provide it to your model, and if you train your model only on the real data and evaluate it on the test set, you see the performance of the model in the first row. So just look at the numbers there: 78, 78, 47, 92, 68. Right? Now, we applied our our Gen AI model and generated the synthetic samples. The next model that we trained was only on the synthetic data. We did not use the real data for training the model. Now, if we use only the synthetic data for training the model and evaluate the classification performance on the test set, which was all real data, you see the performance in the second row: 75, 72, 46, 91, 67, right? So what do you observe? What's happening here? Like, what's different between the first row and the second row?
Yeah, so the model trained using synthetic data has on-par performance
Right.
with real data.
Yeah, so even though it's slightly lower, we can see that it's quite well. It's coming quite close to the model performance, to the model that has been trained on real data. So what this tells us is that the synthetic data has actually captured some of the phenotype, some of the phenotypic properties from the real data, and that is why we are able to achieve performance that is quite close to the model performance that was trained on the real data. Now, interestingly, if you combine the real and synthetic data for training, so you take the training data set, the training data set that has the real samples, you augment that data set with your Gen AI model. So you have now generated samples. your synthetic samples, you combine the real and synthetic data for training and then evaluate it on the real test set, we see that there's quite a significant jump in performance, right? Look at the third row. So what this tells you is that even if you have, let's say, so one of the questions that I get, and I'm sure many of you will have this question if and when you get into machine learning, how much data is enough for training? Like I've been in this field for more than a decade now, more than 15 years now, close to 20 years, but I don't have that answer yet, right? So we don't really know how much data is enough. It depends on what the clinical problem is, or what the problem is, what the classification problem is, what the detection prediction problem is. Sometimes data points in the order of hundreds might be enough, and there will be times where even with thousands or tens of thousands data points, you might not even get good results. Okay, so doesn't matter what it is. What this tells you is that if there is a scope to augment your real training data with something that, with your synthetic data, which obviously has to look similar to your real data, it cannot be something entirely different, that could potentially be an avenue to augment your data set and potentially lead to better model training. Another lesson here is look at the distribution of the training set, or look at the distribution of the diseases in the data set. So you have what, 1000, 800, 1400, 600, and then 700, 300, 800, 273. So clearly the adenoma case, or the adenoma class here, has fewer samples compared to the other classes, right? So there's a class imbalance here.
So I have a very basic question.
Yes, go ahead.
So we should take a macro average or weighted average, while calculating the F1 score, or precision or recall. Because
right.
I think this is a weighted average, right?
Yes. Yes.
We should take weighted average or macro average, because in macro average is very less. When you compare to from weighted average to macro average.
Right. So that's a very good question, and I'm glad that you brought that up. So it depends on if there is actually a class imbalance or not, and depending on that you can decide what to take, right? So most of the results that you see here are all weighted averages that we are showing.
So should we provide two?
You can provide both.
Both.
You can provide both. Yes.
Because most of the papers right now also they are only putting the weighted average.
Right. And the other thing, so that's with your F1 scores. If you are reporting accuracy or AUC, report that, but you should also report something called balanced accuracy.
Balanced accuracy.
Right. Balanced accuracy, balanced AUC. That's when you actually. That's when your metric reflects the class imbalance.
Class imbalance.
Right. So that's a good point that you raised here. Yeah, so it's clear that we have some level of class imbalance here. Now, if you look at the performance of the model for adenoma, you see that when you combine the real plus synthetic, and I'm talking about this column here, you see that the performance improvement for adenoma classification improves significantly. So what this tells you is that for cases where you have severe class imbalance, you can apply GenAI techniques to artificially augment the data set, and hopefully your performance will increase, right? And this is especially true for these less represented classes, because we do not have enough samples to train our model. Okay, so next we'll see how we can use another modality associated with pathology, and that's called text. So similar to radiology, where we have radiology images and we have the corresponding radiology reports, with pathology we also have the images and you have the corresponding reports. And in the reports, what you have is the pathologists basically look at these images and look at, it's not just one slide. Since it's a chunk of tissue that has come out, you section it, there'll be multiple sections. So they look at multiple sections, and based on what they see, they come up with a consolidated report. So TCGA doesn't just have images and omics data, it also has text data, by the way. So you can look up just fire up TCG on your browser. You can look at your some of the text reports that are out there, and you'll get an idea about how these reports look like. I have some examples later in my slides. So whole slide images are accompanied by extensive pathology reports. So what we do is we use these reports as global level conditioning information about the image. So these reports will tell you what's happening in the image as a whole. I mean, they might have some information as to, okay, this is, left side of the image shows something, or the right side of the image shows something, but there won't be any annotations per se, right? It's a report, so it's all in text format. So this report will give you a global understanding of what's going on in that image. Now, obviously, pathology, like we saw, it's so much information. You have, if you remember, we zoomed in yesterday, starting from a local scale to a global scale. At the local scale, you saw the texture of the cells, the shape of the cells, the morphology, and as you keep zooming out further, you'll see how these cells are arranged with respect to each other, and then you zoom out further, you start to observe how the shape of the whole slide image is, right? So you have different levels of information. So, which means that if you patchify them, if you patchify the data set, you divide it into tens of thousands of patches, because these are huge images, and if typically when you look at deep learning models, you'll have patch sizes like 224 cross 224 or 512 cross 512, usually around that range, nothing bigger than that. So if you have patch sizes like this, and these images are 50,000 cross 50,000 images, you can have so many patches from these images. Now, let's say that you have trained some sort of a patch classification model where you are quantifying the amount of till in every patch, or the amount of, let's say, necrosis in every patch. So from there, you can get a patch level information, and from the reports, you can get a slide level information. So the idea behind this project was to combine patch level information with slide level information to build a generative model. Okay, and I'll show you how we do that. So first, for the slide level information, we get the report, the pathologist report, and it can be a very detailed report, or it can be a short report. Sometimes, a lot of times it's in a structured format. There are CAP guidelines, Association of Pathologists, so they have those guidelines. If they follow those guidelines, then you'll have a more structured report. Otherwise, a lot of times these reports can be free text. There's no structure to it. It'll be just like them explaining what's happening there without context. So what I mean by structure is that, let me ask you this question: what's the difference between a structured report and an unstructured report?
Like there is some sections, and there is some entry points, right, where they have to enter some value.
Right. So if you look at, let's say, if you have ever looked at blood reports, you'll see that there'll be certain sections, and the values get filled in there, right? As opposed to, let's say, maybe back in the day when you did not have structures like this, there'll probably be a sentence saying that, okay, your cholesterol level is this, your sugar level is this, something like that, right? So it can be either in a structured format or an unstructured format. So whatever format it is, you can provide it to a large language model, and you can get a summary. So the large language model will summarize it for you, and you can ask the large language model to summarize it for you in a way that all the reports, when it summarizes them, they follow a similar structure, right? You can create your own structure. That's what I mean. So let's say that you create your own template, and you ask the ChatGPT, you ask your large language model to take that report and fit it into your template. That's all we did. And then, so that was the slide level information. Next comes the patch level information. So I showed this slide yesterday where one of our colleagues developed a tumor till classifier, where we had we had a model that would quantify how much tills or how much tumor each of these patches had, and based on that we just did a a dichotomous thing: high tumor or low tumor based on some threshold that we chose, and high till or low till. So each patch had these values. So maybe 1 0 0 1 1 1 0 0, right? So let's say tumor till. So till low, till high, till high. So basically high low, low high, high high, and low low, right? So it's a very simple thing that we designed. So once you had that, so this is basically what I just spoke about. So now you had a patch, you had patch level information and you had whole slide level information. So you can provide that this information as a conditioning strategy to your diffusion model. So diffusion models, you can condition them with information like this. And we did that, and based on that, we generated the output for each of the patches. And here are some of the results from a quantitative perspective. So we achieved state of the art in image quality. We surpassed some of the previous efforts. FID, if you remember, I introduced the FID concept, where FID is used to evaluate how good the image is. So lower the FID score, the better it is. So we were able to obtain an FID score which was lower than some of the other methods. And interestingly, when we combined the slide level information with the patch level information, so if we did not have the slide level information, the FID was high. If we combined the slide level information, the FID was low. So this means that entire context means something, that when the maybe the pathologists also tell us something that is not directly visible in that image, right? Some sort of conclusions that they draw based on what they see in that image. That is not there directly in that image, correct? So just an illustration of what's there. Yeah, so here's the report. So here's the report from TCGA, and this is the prompt that we gave to the LLM, and the LLM generated an output like this, and then we asked it to make it more succinct, right? We asked it to summarize it, and this was the result. This was provided to the language embedder. We got the embeddings that was then used as the slide level conditioning. So here are our results, qualitative results. We see on the top row, you have the real samples, and then in the second row, we have the path LDM, which is our method, and we can see that results, the generated patches look quite similar to the real patches. Then back then, we only had 3 methods, or 2 methods rather, for comparison. So med diffusion and this one. And we showed that our method was quite better compared to these other methods from a qualitative perspective as well. And one of the things that we observed with other methods is that there were a lot of artifacts. Again, these artifacts can be brought about by in many different GenAI methods, and our methods did not have these artifacts. So this is also interesting, because most AI methods, most GenAI methods will have some sort of artifacts or the other. I'm sure that if we did a detailed analysis, our methods would also have some artifacts, right? So what this means is that when we evaluate, or when we apply, when we train our GenAI methods, and when we are validating it, this again falls under that category of error analysis. So identify what these misclassifications, what these artifacts are, and look at these artifacts. Compare these artifacts with artifacts that other methods develop or show you, and then maybe also sit with your clinical collaborator and talk to them, ask them to interpret what these artifacts might be. This might be just nonsense artifacts, but maybe there's something you can learn from that as well, right? So this is also very important, which a lot of research works don't do. Okay, so what we saw in the previous project was we took these representations coming from the reports, which is at a whole slide level, and we take these representations coming from the patches, which are essentially classifiers that we trained, and use these representations, the slide level representations and the patch level, whatever till tumor scores that we had to condition our GenAI model. But this might not be feasible always, right? Maybe you don't have a classification model, or you don't have reports, which means intrinsically this data becomes unlabeled, right? So now you have unlabeled data. How can we still train a GenAI model to do what we want to do? So how we do that is by using our foundation models. So we have the foundation models that you saw previously, Phycon or Virchow or Conch or some of these other models. So when you apply, when you run your patches through the foundation models, you will get a representation, right? So now you can use that representation to condition your diffusion model. You don't need to have a tilt tumor classification, or you don't need to have a textual description of what's going on in that image. You have your foundation models, apply your foundation models, run your your patches through the foundation models, and you get the representations, you get the embeddings. Those embeddings become conditions to your diffusion models, and we did that here. So based on that, we see that the quality of images that we got were quite good, and it represented. So we basically, what we do here is we propose using the representations learned with self supervision in place of human annotation. So this was what I just discussed. So this can help us learn to synthesize images that are similar both in appearance and semantics of the reference patches. So just an observation here. So a lot of this, in fact, what I'm explaining to you here is using images as examples, but you could do this with any modality of data. If you have text data, if you have sensor data, you can use all of these techniques to do this, to essentially augment your data set. So by that, what I mean is, so let's say that you have an array of sensor data. You can, if you have foundational models that have seen sensor data, you can extract representations from your sensor data. You can then use these representations, you can use these embeddings to generate synthetic sensor data. And now this synthetic sensor data can be used to, let's say, fine tune your model or further refine your model. Okay, does that make sense? Okay, we also had other projects, another project where we tried to do a multi-scale generation, because we know that single scale is not enough. So we can have representations at 5x, at 10x, at 20x, 40x, and so on. So we can always take contextual information through foundation models that have been trained at different resolutions and provide multi-resolution embeddings as conditions to your diffusion models. That's what we did here, and we have a multi-scale generation technique. So using the multi-scale features, we can boost the performance of the multiple instance learning tasks that we saw in the first half of today's lecture. So here's some recent work. This is currently under review at Nature BME. So here we are. So for the first time, we proposed a foundation model from a generative AI aspect. So it's a generative foundation model for digital pathology images. The code is out there. Feel free to look it up. So what you can do is you can take images, and then you can use our proposed framework to generate synthetic images. And we also have made the dataset public. So we have 1 million patches that we have synthetically generated, and you can use these for your model training. So there is another aspect to it that's very important. A lot of times, so how many of you are familiar with the concept of federated learning? So some of you here, right? So a lot of times, when it comes to collaborations, so let's say that you're developing your model here at NIT Rourkela, and you have your collaborators somewhere else, let's say on the other side of the continent, or you have, let's say, even collaborators at hospitals elsewhere. For some reason, they don't want to share the data with you. I mean, obviously, sharing of data it's not straightforward. There's a lot of ethical issues there. In the US, we have this HIPAA considerations. There's patient privacy information, and a lot of legality there. And a lot of times it gets very tricky to share data, share images, or share any medical data. So federated learning, just a very high level description is, you don't have to share data. What you can do is you can share model weights. So let's say that that there are like these three rows here, and I'm an aggregator. So each of these 3 rows have their own data. So you train your model, and you train your model. and you send me the model weights. Don't send me the data, send me the model weights. I have some sort of an aggregation strategy. I will, using whatever aggregation strategy I have, I'll combine these model weights, and I will push updated model weights to each of you. And then with those updated model weights, retrain your model for the next, for the next bunch of epochs. You will have new model weights, send them back to me. I will now update them, and obviously I have a validation that is running on my side. When I'm happy, I will tell you that this is my final model weight, use it on your side, right? So you don't have to share your data with me, just share your model weights with me. So that's a very very high level description of what federated learning is. Now sometimes even that may not be feasible, right? Even federated learning may not be feasible. So then what I can do, so let's say that 3 of you are collaborating. So what you can do is you can take your real data and using some Gen AI techniques, generate a synthetic version of your real data and share it with your collaborator, or share it with me if I'm your collaborator, right? You can do the same thing, generate a synthetic version of your data and share it with me. So you are not sharing the real data, you are just sharing the synthetic data with me. Okay, so that's something that can be done as well. And we have actually shown the feasibility of that in this paper. So this paper actually we used close to, there was a question regarding how many slides are enough to train a foundational model. We had about 70,000 slides, and this was a model that we trained. We had multiple different cancers here. So the other thing about foundational model is that you don't need to stick to just one kind of domain, one kind of organ, right? So we had about 10-15 organs that were represented in this foundation model, and this is where we are illustrating how we can do privacy preserving synthetic data generation. So similar to federated learning pipeline, and other things that we have shown that could be done using this foundation model is stain translation. We have taken H&E stains and translated them to ER, PR, key 67 stains, basically IHC staining. So virtual staining using our foundation models. Okay, so there is something else that is important here. Yes, we can take the representations that your foundation model representations, use that to condition your diffusion models and generate synthetic patches. But like we would hope, and obviously some of this is happening, that these foundation models, in some sense, because you have different layers of your neural networks, they will encode the nuclear layout, the morphology in some sense, right? We don't know how it is happening, but it is happening. But how about we explicitly give that as a condition, right? So by that what I mean is, you on the left of in the first column you see centroids, which can be essentially the centroids of the different nuclei, or they can be centroids of other primitives. Can you use the centroids as conditions to generate your image? That's what we did here. We just provided the centroid and we asked the model, okay, can you take this centroid map and generate for me a patch of breast cancer image, right? And that's what it gave me. What you see here is that you will see that the nuclei are exactly in the same position as the centroid map. Now there are obviously multiple uses here. Let's say that for certain cancers, the topology or the spatial layout of the cells looks very distinct from another cancer. Now you want to use it as a teaching tool. So you can take that topology, that layout, and ask the model to generate multiple examples with that same layout, right? So you can use that as a teaching mechanism, as a teaching tool for pathologists. And what you can also do is, if there are multiple kinds of cells, and that's what you see in the third row. So you have neoplastic cells, you have inflammatory cells, epithelial cells, and so on. So it's a multi-class layout condition generation. So that's what we have shown here. Okay, so some of you here are working with transcriptomics, right? What if we can actually infer the molecular state of a tumor directly from the histology image? Why would we want to do this? Why do you think something like this will be helpful, inferring the molecular state or the omics directly from a histology image?
It will give you the level of the gene, how the tumor is progressing. You will get that idea also. Generally, if you have just the genomics data, you don't get how the tumor is progressing.
Okay, so that's Yeah, that's true. So since you have two levels or two modalities of data, you can do some sort of association. What else?
So typically, it's easier to if you are able to train a model which can infer the genomics. So genomics is more expensive
Expensive.
in terms
Yes.
of
Right. So, like you already know, it's very difficult and very expensive to get this kind of data. Even if you have facilities here to, let's say take tissue samples, you might not have sequencing capabilities. You'll have to ship your tissue out somewhere else. They'll do that. They'll send it back to you. So what if, and we briefly discussed this yesterday, so what if you can do this on site? So if you have your images, can you use your images or can you use your tissue to directly infer the molecular state? So integrating gene expression with histology can give us information regarding both cell states and morphology, and eventually this can help in improving risk stratification and help in better treatment planning. So here I would like to introduce the concept of spatial transcriptomics. So usually in your genomics, in your transcriptomics data, you have a bulk level sequencing where you have your omics data is representative of the entire sample. But with ST or spatial transcriptomics, you have omics data corresponding to each patch or each spot of the image, and this is more granular compared to bulk level sequencing. Okay, so you will see that there's a lot of research going on on ST right now, because this actually helps you quantify the heterogeneity of the omics profile in a given tissue. So predicting the spatial gene expression from routine histology, it can enable scalability, low cost molecular profiling, and eventually we would want to get to discovery of image-based biomarkers without sequencing. There are a lot of baseline methods where you have image encoders and then you have gene encoders. So you'll see that there's a lot of tools out there, a lot of techniques out there that have used transformer based backbones to encode gene representation. So one of them is called a DNA BERT. DNA BERT, it was actually developed by a faculty, a group in our department. So what it does is you can take your expression profiles, provide it to this BERT model, and it would give you the representations. Anyways, so there are this and there are other models out there that can take your gene information, encode it, and then to develop a model you can do a contrastive learning between your image and your gene representations, and then when in your inference stage you can only have the gene information, or you can only have the image information, and you can predict the gene. So this is what a lot of methods have done. But for those who are actually working with gene data, you know that these don't work in an isolated manner. There's a gene-gene interaction, which leads to different expressions of different pathways. You probably know that better than me. So what we want to do is, when we train these models, we want to take into account the interaction between the different genes. And one way of doing that is understanding what the pathways are, right? So what we wanted to do here is, instead of doing, so Moinak was also involved in this paper, so instead of performing this contrastive learning at an image and gene level, we wanted to perform it at an image and pathway level, right? Because we know that these pathways are eventually what drives the pathogenesis of the disease. How did we do that? We took our images, we patchified it, we provided it to an image encoder, which can be any foundation model. We got the embeddings, we got the projection using some MLP head, and we also had the gene expressions. We did a gene set enrichment analysis. Then after that, we identified the pathway scores, and we did a pathway embedding. We again had a projection, and then we did a contrastive learning between the projection coming from the image head and the projections coming from the pathway head, right? And in the inference stage, we had only the image. The image would then be provided to a gene MLP and a pathway MLP, and it would compute the gene expression scores and the pathway scores. So that's the model. So this was just recently accepted at VACVI. So how can we use this? So we can use this now we have, let's say, a foundation model that has seen what pathway scores are, how they relate to images. Now we can use that for downstream survival analysis instead of just image-only models. Okay, so there are data sets, and you see newer data sets being added right now because ST is a hot topic nowadays. So we used this HEST 1K data set, which had not many samples, couple hundred samples, in fact less than that. So breast cancer had 36, skin cancer 12, lymph node cancer 24. But still there was enough data for us to train a model, and if you're interested, you can always look up this data set. Before this, the models that had been trained or that were out there to do gene expression prediction were STNet, His2ST, BLEEP, and MCLSTX. So these 4 models, and these 4 models did not consider pathways. And we saw that when we considered, or when we took into account the pathway scores for our contrastive, learning, we found that the performance and the metrics that we used were the Pearson correlation coefficient, the MSE, and the so absolute error and the mean squared error. So these were the different metrics that we used, and across the board for breast, skin, and lymph cancer, we see that our performance was much better compared to models that did not take pathways into account. So what this tells us is that just the nature of the disease, just how biology works, they don't operate at a single gene level. You have gene-gene interactions, because of which you have upregulation, downregulation of different pathways, and that leads to a disease progressing a certain way. So if we take that information into account to the best extent possible, I'm not saying that this is the only way you can do that, that has been shown to improve performance of gene expression classification. Qualitatively, on the top row you see the pathway scores, and on the bottom row you see the gene scores, and ST is important because again you have these scores for each spot in the data set. So you see that, okay, so let me start with the gene scores first. So this is the ground truth, and this is second one is ours. You have the other methods here. We clearly see that our method, the expression scores, obviously visually it's quite similar to the expression level of the ground truth, and you see that not just for the gene here, and the gene that we considered here was this one, which serves as a marker for immune activation, and this is one of the genes that is that's there for the hallmark allograft rejection pathway, and that's the pathway score that you see on the top part of the screen, and you see how ours is quite similar to the ground. I'm not saying it's perfect, and if you look at the quantitative scores, you'll see why. You'll see that that's reflected there. PCC of 0.58 is okay. It's not great, right? But it's still better than the other methods. Similarly, it's still quite low, but it's similar to the ground truth, at least from a relative expression perspective. This is another gene which is a marker of stromal activation, and we see how that gene, the expression level, is quite good for our method compared when you compare it with the ground truth, and the corresponding pathway here, which reflects the aggressive tumor behavior. Any questions? Okay. So what are the takeaways? So we propose a pathway-based representation of ST data, and this can enable biologically enriched embeddings for multimodal learning. And you see how the theme of interpretability keeps coming up again and again, right? I mean, yes, you have interpretability at the gene level, but if you talk about it from the pathway level, clinicians start to understand it even better, right? Biologists start to appreciate it even more. So we designed this multimodal framework. It combines this transformer pathway encoder, an image encoder, and contrastive learning to predict both pathway and gene expression scores. And we evaluated it on multiple different data sets, and we showed how our method, which we term Pearl, it outperforms the other existing approaches. So now what we are doing is we are extending this to a pan-cancer setting. So the models that you showed there, they were individually trained for the different cancers. So now we are trying to come up with a way to combine different cancers and come up with a true foundational model for gene prediction and pathway prediction. Okay. So reports, coming back to reports, I know that I've been switching back and forth, But this is more recent work, unpublished, but we took part in this Mikai challenge and we scored the 3rd position. So this challenge was about taking slides and generating reports from it automatically. So there are many different methods. I mean, not many different methods. There are a handful of methods out there that can do that. But what we wanted to bring in was, yes, we can use foundation model representations and use that to generate reports, but we wanted to bring in some interpretability. And in this case, since we had our published work Gecko, we wanted to see if we could use Gecko to bring in some concept level interpretability here. So the objective was, given a whole slide image and short pathology report pairs, can we develop machine learning models to generate these text reports? And this is a data description, 7 different tissue types. They were collected from 5 different institutions, and this was from multiple different countries. This was actually organized by a few hospitals in Asia. Here are the different, and this data set is again public. You can always use this data set. So you have the different organs, stomach, prostate, lung, colon, cervix, bladder, and breast. These are the number of cases. And for different organs, you had different diagnostic categories as well. And the goal was to classify the tissue into these diagnostic categories. So you needed to classify what organ it was, what was the diagnosis, and something else. I'll look at that in the next slide. Yeah. So here. So 2 samples. The first whole slide image on the top, it belongs to colon. What was the procedure? I mean, that's not really necessary to be denoted in the report, but they had it, so we had to train a classifier for that. But this is not that important. You had the procedure, how it was taken, and then what was the diagnosis? So it was a tubular adenoma with low-grade dysplasia. And for the second one, it came from the breast, a sono-guided core biopsy, and the type was invasive carcinoma. It was diagnosed by the pathologist, grade 2. Sometimes there might be other kinds of grades like mitosis, nuclear grade, tubule formation, and so on. So bottom line, it was a very heterogeneous data set. Okay, so it was not a similar level of information for all the diseases. So how did we approach it? First, we extracted visual features and integrated it with a transformer encoder-decoder network for generating these reports. We use multiple different foundation models. So the reason we use multiple foundation models to encode the imaging representations is because all these foundation models are good. You'll see that some foundation models outperform the other on certain tasks. Other foundation models are good on other tasks. So which means that they are capturing, in some sense, some complementary information. So we wanted to see if we could take these different information and come up with something that was reliable, that was robust. And we also used concept grounded features from Gecko, and after that we used some perturbations to come up with some agreement logic. I won't really talk much about that, but I'll show you the overall architecture. So you had the whole slide images, you divide it into patches, and then you apply different encoders, like I said. So Conch encoder, this was developed by Dr. Faisal Mahmood's lab from Harvard. They're actually one of the really good groups when it comes to developing these methods. They have access to a lot of data. They have a lot of models that they've made public. So a lot of researchers actually use their models. They use their models. So this is a Conch model. The architecture is built on a VIT backbone, a VIT large backbone. There was another model called the Titan model, which is a multimodal model. So Conch is, so Titan actually, I believe it used gene and images. So that's why it's a multimodal model. And then we had a Gecko model. Gecko uses what? It uses images and text, right? So it uses the concepts that we discovered. So you have these different representations, and then you provide it to a MLP adapter and mixer. So it basically comes up with a consolidation. It combines these different representations that are coming from these different models. And after that, there's encoder-decoder framework, which was inspired by another work called MIGen. And then we use that to predict or to generate the text. So Gecko, I don't need to introduce that further. This is how it works. I had shown that to you earlier. Now, how did we identify this concept? So we spoke to our pathologists, or we provided, like I said, we first provided the, we identified literature, provided them to large language models, identified these concepts, and cleaned these concepts up by discussing with pathologists. So these were some of the breast-related concepts on the top: the cribiform pattern, papillary structures, and lung-related concept, lepetic growth, keratin pearls, prostate, cribiform, and so on and so forth. So I'm not saying that these concepts are perfect. We are still working on refining these concepts, but eventually we would want to get to a point where we have concepts that can actually describe these diseases to the best extent possible. Now, so on top in the red text, you see the ground truth data for a particular case. It's a prostate biopsy. The diagnosis was acinar adenocarcinoma, and Gleason score. So Gleason grading is what is typically done in prostate, which tells you how aggressive the disease is. So synoptic report is a format where you can actually make it more structured, right? What's the biopsy site? Prostate. What's the mode? Biopsy. What's the diagnosis? Acinar adenocarcinoma with Gleason grade 7. What's the tumor volume? 90%. So right. So you take an unstructured format and make it into a more structured format. And on the lower left side, you see what our model predicted. You see that it's quite good. Just that there was some difference in the Gleason pattern, but it was pretty good, and we stood third in the final leaderboard. Okay, so there was an interesting lesson here as well. I'm pretty sure that the model that we developed, we would have outperformed the other model, but there was some mistake that we did. So in the first round of evaluations, our model scored very poorly. Like we were like 6th or 7th on the leaderboard, and we couldn't figure out what was happening, because we saw the results. We like qualitatively, by qualitatively I mean that we saw the predicted reports, we saw the real reports. They looked very similar to each other for a bunch of cases. We had no idea what was going on. Then, so this my student who's working on this, Suryakant, he figured out that there were some metrics. There were a few metrics that they used to evaluate, right? And these metrics are more NLP based metrics. Our results were all in small case, or the first letter of the word was in capital case, and the ground truth was all in small case, or something like that. So there was a case difference, and that led the metrics to fall drastically. Right. So which means that when we trained our model, what we should have done is we should have converted everything to lowercase, and then also the reports, the generated report should have everything in lowercase, and then we should have evaluated it, right? So we did not. It was a very silly mistake, but it cost us. So, right. So these are the kinds of pre-processing steps that you have to make sure you do before you train your models. So these were the different scores, Rouge, Meteor, similar to what we saw for radiology. We have the same similar scores for pathology as well, and these were the performance of our methods. Okay, now how can Gecko improve it? So this is what you get from, this is the generated report that you get, that it's a breast tissue. The biopsy was a core needle biopsy. The diagnosis was a ILC or lobular carcinoma in situ. You have microcalcifications, so on and so forth. Now, using Gecko, we had seen how it can tell us what are the top activated concepts. Right now, you can provide this to your LLM with your generated report, and you can ask it to generate a more like an enriched explanation. Right. So now what you see is, yes, we can provide you the reports, but we can also provide you additional explanations as to what sort of features your model actually picked up on, what sort of features, what sort of concepts were overactivated. I mean, for all you know, these might not be useful for pathologists. The pathologists will still stick to this kind of a report. But from an interpretability perspective, like for us, we know what were the features that led the model to calling it a particular disease, it diagnosing a particular class, and so on. Okay, so coming back to QC, so one of the QCs, so why I have this QC slide here, it was actually motivated by that error that we made where, you know, the lowercase, uppercase thing. So garbage in is garbage out. We have to make sure that our data sets have been properly quality checked before we provide them to our machine learning models for training. So there are models out there such as HistoQC, which was developed in one of the labs that I had worked previously. So when you look at histology slides, we saw that there can be out of focus areas, right? And there can be other things as well. So a lot of times what happens is when you prepare the slides, you'll have crack on the slides. And when you digitize it, that crack looks bigger and it blurs certain regions, right? So, and when you, if you don't consider this in your model training, and if you provide the patches that have cracks and say that it's a cancer patch or it's a normal patch, obviously the model is learning from those crack pixels. It's not learning from the actual, you know, underlying tissue image. Similarly, interestingly, you know, I've heard from one of my colleagues that there was a hair that went into one of these slides, like while they put the slide cover on, and that seemed like, okay, it was a part of a tissue, right? So these things need to be removed. There can be air bubbles. These air bubbles can be confused with, I don't know, some glandular structure or something, right? So we have to make sure that these portions are removed, or if you have methods like superdiff or other sort of correction methods, try to apply these if possible. So similarly, there are methods that people are developing, you know, CT, QC, there's a MRI, QI or QC, there are other methods out there that can be used for quality control of radiology images as well. Okay, so coming back to our immunotherapy response prediction project that we have been seeing over the last 2 days. So we saw how we can extract radiomic features or radiology markers, but we can also extract pathology features, right? So we can extract where the lymphocytes are. We can look at how the lymphocytes are, how the cancer cells and lymphocytes are co-located with respect to each other. So what we did here is that we did a correlative study, and we saw how there are certain radiomic features that are associated with pathomic features. So the reason we did that is, why we did that is because we want to get to a rad path setting where we can tell the doctor that because of certain, you know, expression patterns of the pathology of the primitives that you see at the pathologic length scale, that is reflected on the radiologic length scale, right? So it gives us like a multimodal, a rad path setting. So that's what we want to eventually get to, a rad path synergy. So with radiology, what do we have? We have a larger field of view because it's a more macro sort of a picture of what the disease is. You have better anatomical and better functional characterization, and you get progression information. Now in pathology AI, you have better spatial resolution, you have more morphologic and mechanistic information, and you have better molecular insights. So finally, we would want to get to a rad path synergistic AI where we can do a true cross-scale characterization, which can lead to a more comprehensive phenotyping. So you have imaging information, you have pathology information, you have omics information, you have, you know, like transcriptomics data. So you can combine all of this data to come up with a more holistic description of what that disease is. And eventually, we hope that it can lead to improved workflow efficiency. So with that, again, thanking all my lab members and the computer vision group.